Hey friends, it's Ben again. This is a video for Calculus 1. We are taking a look at trigonometric limits. Okay. One of the big things that you'll see in the section is some talk about the squeeze theorem. And the squeeze theorem is a super important result, but it doesn't have to be used in every problem. So please bear in mind the squeeze theorem is just really super necessary for one super important limit. And then once you've got that, most of the rest of them you'll just do from a little bit of algebra and the 2 or 3 special limits from the section. Okay. All right, so let me jump right into it and share the screen here in order to talk about what we're doing with these limits. All right, so off on the left-hand side of the screen there, you'll see a limit where you're taking the limit as x goes to pi over 6 of x divided by the sine of 3x. Now, one of the things that I always tell y'all is try plugging in the numbers. If it works out, you don't have anything more to do. So in this particular problem, we are well drat it. Okay, we are trying to plug in pi over 6 to the x. And of course, on top, you get just pi over 6. On the bottom, we worry a little bit more because we might be getting a 0 on the bottom, right? If you get a 0 on the bottom but not on the top, then you need to look at a graph to see what other things might be going on. But in this case, we've got pi over 6 divided by 1, because 3 pi over 6 is pi over 2, and the sine of pi over 2 is just 1. So that means this limit here is just pi over 6. So if you get a limit like that, just go ahead and accept it. If it turns out to be something where there's a division by 0 and you've got a limit here that does not have one side or the other, then you've got to take a look at your graph. If both sides agree and it's going to positive infinity, then your answer is positive infinity. If they agree and they're both going to negative infinity, then your answer is negative infinity. But if they disagree, then you say that the limit does not exist. Okay. So some textbooks will have you saying that the limit does not exist even though it is positive infinity. And that's kind of a philosophical thing. Does infinity exist? Well, I mean, does the square root of 2 exist? They're kind of, you know. All right. Anyway, so with regard to that sort of limit, if you're running into those, try them out, see what happens, and you can figure those out without too much more. But the tricky thing from this section is really squeeze theorem stuff, all right? The idea of the squeeze theorem is actually kind of intuitive. And I have the suspicion that you're not going to believe me on that one. But it says if you've got 3 functions and one of them is in the middle, and you're able to take a limit on the other 2 functions, and that limit goes to the same thing, then the function that was between those 2 has to go to that same thing. See what I mean about intuitive? It just says that if you have 2 places, 2 kind of fences here, and the function that is kept between them has to go through this one spot, then that's the only spot it can go through. So this just allows us to do some of the limits that we couldn't otherwise. In particular, this one here. Now, the limit that we're going to get out of this is 1. One of the questions that you are probably going to ask me is, do we have to do this squeeze theorem stuff every damn time we see one of these limits? No. You can look at this sine theta over theta. After this, and say, aha, that's my special limit, it's going to go to 1. But you as a calculus student need to be exposed to this particular thing here because it's kind of an interesting argument, okay? So we are going to establish that the sine theta over theta, as theta goes to 0, is going to turn out to be 1. If you take a look at a graph of it, the graph would end up being something something that looks somewhat like this. So it oscillates on either side, but here at 0, it seems to be going to 1. Now, if we're talking about doing things graphically, that's often good enough. In particular, if you're not in a math class, but in a science class and needing to deal with these things, you would just use it. But we need to put things on a little bit more of a sound footing here. So the thing that I want y'all to spot here is actually, let me see if I can indicate it here in a way that's easy to see. We're going to establish something geometrically. If you take a look right here, and of course, it did not do what I wanted it to. So I'm trying to draw this triangle there and let it shade in. All right, if you look at that, that triangle there, it has a height on it like so, that's going to end up being sine theta. This is because we're going to think about having a circle, a unit circle here, like so, and then the points that are on that circle will have the coordinates cosine theta, sine theta, all right? And so consequently, this height that you've got right here is going to be that y coordinate of this point. And so that's why the height of it is going to be sine theta. The base of it is going to be 1 because the radius of the circle is 1. And so you get the area of that triangle with 1/2 sine theta. And we're going to see that that is the smallest of the areas that we're going to talk about. Let me see whether I can remove this piece now. I can, oh, great. I can't, so. All right, let me back this up here and try to take the shaded area off. Okay, now the other shaded area, the other area I want to shade is that middle area there. If you take a look, and it will not do that no matter what I do. Okay, so I will need you to use your imagination. That sector of a circle there with that area or with that angle of theta, we actually have a formula from a trigonometry class that would be like in the first week or something of a trigonometry class. So you're forgiven if you've forgotten it, that the area of a sector with an angle of theta is going to be 1/2 of theta. Okay, so that's the reason for this part here. But then the sector of the circle is going to be inside of this other triangle here that has a base being 1, but the height of it here is a little bit tougher to figure out, but it turns out that that height is going to be the tangent of theta. The reason for that is because of similar triangles, that you would take this smaller triangle that had the height being sine theta, and you would divide by cosine theta and end up with that there, okay? But in any case, we end up with the inequality going across like that, right? So once we are to that point, then we're going to make this observation that if you take the first piece there and divide out, then you will end up having that sine theta divided by theta is going to be less than or equal to 1, okay, by dividing out the 1/2 theta. So remember that that part comes from the first half, okay? And then for the other part of it, if we, I've kind of lost my place here a little bit, but if we take this second half here and divide the 1/2 out, of course you got theta being less than or equal to the tangent of theta, and then if you look at that as being sine theta over cosine theta, then you could take and multiply both sides by cosine theta, and then divide both sides by the theta, and get this. So that would tell you that in this inequality here, that we can put the sine theta over theta to be greater than or equal to the cosine of theta, okay? And then, because we can take the limit as theta goes to 0 of cosine theta and just plug in the 0, we'll get 1. And that then collectively tells you that the limit as theta goes to 0, sine theta over theta equals 1 by the squeeze theorem. And theorem. Okay. Now, that's kind of a neat little result there, and mostly we're going to use the heck out of it. But a lot of times people look at this and they say, I don't know if I really understand everything that's going on with the squeeze theorem. So let's take a look at another example, okay? So the main thing that you would have to look for in squeeze theorem examples is that you have one term that you just don't know what the heck to do with. In this case here, we've got x going to 0 and this cosine of pi over x happening. So if I drew just a super quick sketch here of what's going on with that function, it's going to do something like this. The other day, somebody asked about an example where where a limit just failed to exist. And this is the typical example for that. It limits in on every possible value between -1 and 1 as your x is going to 0 from the right. So that tells us that we really can't deal with that part there, okay? But we can say this, -1 is less than or equal to the cosine of pi over x is less than or equal to 1, okay? And then because we've got that exponential in there, e to the -1 is less than or equal to e to the cosine pi over x which is less than or equal to e to the 1. So e to the minus 1 is, a little more than a third. And e to the 1 is like, e, so a little bit less than 3. So what, what that says is that we've got these two numbers. I'm going to go ahead and put a number that's just a little bit smaller here, and a number that's a little bit larger over here, okay? Now, if we multiply that through then by the square root of x, then we get that, okay? Now, if you're asking, how do I know to multiply by the square root of x? Well, that's what appears in the function there, okay? I was just going in here and saying, I don't know how to deal with this. I'm trying to now build something where I can deal with it and just get two bounds on it, okay? So because of the fact that we're able to take the limit as x goes to 0 from the right of the square root of x and get 0, then that means the limit as x goes to 0 from the right of 1/3 square root of x, and the limit as x goes to 0 from the right of 3 square roots of x, those will all turn out to be 0. So the limit as x goes to 0 from the right of the square root of x e to the cosine pi over x is going to be equal to 0 by the squeeze theorem. Okay. So the previous example had a big geometric motivation, and it's just an example that we actually need to be able to use for a lot of things that come later on. This example here is not as important, but it shows us the kind of thing that's going on. We have a piece we don't know what to do with, but we can put bounds on that piece. And then we try to build the piece that we actually need out of that and get the inequalities hanging on to either side so that you can actually apply the squeeze theorem. So that's the thing that's going on with that, right? Now, the next sort of thing to look at here is going to be taking a limit that's almost but not exactly the same. We're taking the limit as x goes to 0 of sine of x squared divided by x. Now, if they had both been x, or if they'd both been x squared, we could just say by the special limit, we've got the answer. But since they're not exactly the same, we need to try to multiply by something or something so that this will turn into the x squared. We cannot factor the x squared out and pull it out of the sign. If we could, I totally would. But what we'll have to do for this is instead take our sine of x squared over x, and we're going to multiply on the top and the bottom by an x. The reason that we do that is that now we will have the sine of x squared divided by x squared, and we know that x squared is going to 0. However, it will have this other piece left over here, and I'll write it as x over 1 just so it's more obvious of what was going on. We just moved the factor of x in there so that we had stuff matching up. So we're going to say this is equal to 1 times, and now we're going, what we're doing is to really take the limit of this first piece, and that's why I filled in the 1, and by the special limit. And then we're going to fill into the other piece and take the limit as x goes to 0 of just x, and that's going to be just 0. So this limit turns out to be 0, okay? If you're saying, gosh, I could have done all this by just doing a graph, yep, that's totally true, but it's not what I'm asking you to do. I'm asking you to develop a little bit more of the calculus skills here. So, all right, let's look at another one that is somewhat similar, okay? Tangent of 4t divided by t, secant of t. Now, the reason that I say this is somewhat similar is that if you break the tangent into sine and cosine, it's going to be something that that would have that special limit appearing in it. But you have to do the work to get there. So I'm going to write down here the limit as t goes to 0, and I'm going to go ahead and write sine of 4t divided by cosine of 4t, and then that other piece, that 1 over t secant t. Well, let me rewrite the secant t a little bit there. Okay, so I'm going to write t times 1 over cosine t. Now notice cosine 4t and cosine, well, hey, that's interesting. I have been writing for a little while here on my screen, and it is not showing up on your screen. Let me see if I can get that back. Yeah. I occasionally have this problem that my iPad just decides not to connect. So if you ever see pauses like you're about to see in the video, it's because I'm having to reboot my iPad, and there's no point making you watch me do that. So pausing. Okay, let's see whether that's going to work now that I've done the reboot that it occasionally wants. You may also notice that I've changed locations. Sometimes I have to get to a different location for the network to make this work. I don't know which one it was that did the trick this time. The trick has been done. All right, so I rewrote secant as 1 over cosine t there. And now I'm going to do the limit as t goes to 0. And I'm going to just rearrange this and have the sine of 4t and t. And then over here, I will end up with a cosine of t and a t times the cosine of 4t. And of course, I copied that wrong. Sorry. That should have been just cosine of t over the cosine of 4t. So, all right, now, the thing that you'll spot is that this isn't quite doing what I want it to. Notice that I've got sine of 4t over the lonely old t there. So to make this work out right, I need to multiply a 4 on the top and the bottom, because I cannot factor 4 out of the sine. If I could, I would. If you're detecting an annoyance in my tone, it's because I've taught the same subject about 1 million times, and people want to argue with me and say that they can factor that out. You just can't, okay? So we will have the sine of 4t over 4t. Because those match, we'll be able to do the special limit now. The 4 that was upstairs will just have to hang out and go like that. Now, plugging in the t equals 0, we will have 1 here by the special limit times, and now plugging into the other part, 4 times the cosine of 0 is 1, divided by the cosine of 4 times 0 is still 0, so we get another 1 here. So the limit we end up getting out of this is 4. All right. So that was purposely one that was kind of challenging because you had several pieces of it put together all at once. So, all right. Here is another one that is challenging for a different reason. And I am going to need to, on this, put some parentheses in that I didn't have before, just to clarify. It does not say sine squared in the denominator. It says the sine of the quantity 2 theta. Now, this one is going to require us to know a little bit about our trig identities. So, in particular, the Pythagorean trig identities that everybody ought to know, okay? So the first thing that we would do is to plug the theta equals 0 in, the sine of 2 times 0, well, 2 times 0 is still 0, sine of 0 is 0, so our denominator is a 0, that's looking bad, right? The numerator, we have 1 minus cosine of theta. As theta is going to 0, the cosine of theta has to go to 1. So the top is going to be 1 minus 1 or 0. So we have a 0 over 0 case to deal with. And we have to figure out what to do. Now, if it were set up to be our special limit, then we would have this fixed. So we need to try to get things in that direction. Now, you probably don't spot where we're going to go, but what we're going to do is to multiply this top and bottom by 1 plus cosine theta, right? The reason that we do that is that the top will now turn into 1 minus cosine squared theta, right? So basically, we've done something very much like multiplying by the conjugate. It's not exactly the same, but it's pretty close. And we still have this sine of 2 theta here, and this 1 plus cosine theta. Don't multiply the stuff out in the denominator, all right? So in the numerator, the reason why we wanted to get there is that the numerator can be replaced with sine squared theta, okay? And that is a little bit of progress, because in the numerator, we've got sine squared theta. In the denominator, we've got sine of 2 theta. If it was normal sine theta, we could cancel one of them. It's not. So what we've got to do is to remember another one of our trig identities. Sine of 2 theta can be rewritten as 2 sine theta cosine theta. And the reason that that is nice is that this theta that we've got here can cancel out with one of the thetas above, not both of them, but one of them. So that means we now have a limit as theta goes to 0, sine theta divided by 2 cosine theta, and that's times 1 plus cosine theta. Okay. Now, the nice thing about that is in your denominator, cosine theta is not 0. It is going to 1. So now when you plug these in, you actually get 0 divided by 2 times 1 times, I guess, 2 there. And so the limit we actually get out of this is 0. Okay. This is the method that you tackle things with to show one of your other special limits that looks like this, all right? So this is another special limit, and it turns out to be 0. And I'm asking y'all to work that one out in the classwork. And what I mean by work it out is to essentially apply the sort of things that we were doing right here in order to get some cancellation and get that to work out. All right. So I want I want y'all to figure out how to essentially mimic the kind of thing that I just got through doing in order to get another special limit. Once you have worked that out, then in the future, anytime you encounter 1 minus cosine theta over theta, if theta is going to 0, you can just write down the limits 0. Okay. All right. So let's see what was the next example to look at here. Pi actually, that actually comes to the end of the examples we're going to look at for today. Those were some kind of complicated examples, right? But go ahead and work on the classwork stuff, which you'll look at Monday. But ask any questions you might have about this. And I would advise open up your textbook, read through some of the examples there, not so much the squeeze theorem examples, but rather look at the examples that are talking about how to use the sine theta over theta and the 1 minus cosine theta over theta, those sorts of limits. Okay. The reason that we need to do these is that we're going to soon define something called a derivative, and you have to be able to take these special limits in order to get the derivative of the sine and cosine stuff to work. So, all right, cool beans. We'll see you all in class.